This is the 49th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses set associative caches. The end of video 47 demonstrated a typical problem with large block sizes. We had two variables, x and g, that happened to be placed in memory such that they had the same index but different tags. As a result, they can't be placed in a direct map cache at the same time because you can't have data with different tags on the same row in a direct map cache. I chose this example for the block size video to show a common consequence of choosing a large block size. But, in my opinion, the primary problem here is not the block size, but rather the inflexibility of a direct map cache. Reducing the block size may fix the problem in this specific case, but what would happen if G happened to be at a slightly different memory location? For example, 10F FFFC instead of FFF0. In this case, both the index and the offset are identical, which means both variables are competing for precisely the same spots in the cache. Changing the block size won't fix this. What we need is more flexibility. We'll see later in the video that providing complete flexibility is expensive. But what if we provided a limited flexibility by allowing each byte in RAM a choice of 2 spots in the cache? We model this by drawing the cache with 2 blocks of data on each line. We call this a two-way set associative cache. There's a lot going on in this diagram, so I'm going to step back for a minute and show you the simplified version from the textbook. The important idea here is that each byte in RAM can be placed in one of 2 spots in the cache. For now, I'll call them left and right, but the diagram here has them labeled as way 1 and way 0. Having 2 places helps with the collision between x and g because x and its tag of 7FF can go on the left, and G and its tag of 100 can go on the right. So this flexibility is helpful, but now when we go to access the cache, we need to figure out which side of the cache the data we're looking for is on. We do this by comparing both tags in parallel, and then using a mux to select the data from the column where the tag matched. Notice, of course, that it's possible that none of the tags match, in which case we have a cache miss. This is a slightly more complete version of the previous slide. The main difference is that it shows the mux that's controlled by the index bits. But like the textbook slide, you can see both the left and the right side of the cache, as well as the hardware that checks the tags for each side. And then this piece here behaves just like the mux that passes the correct data back to the CPU. It's structured just like a mux. The AND gates that happen to be attached to tags that don't match produce zeros on all the output bits, and then the one AND gate attached to the tag that does match will pass through the corresponding data. And just like a mux, at most one input to the OR gate will contain non-zero data, so that's what gets passed back to the CPU. Also, to help you follow all the detail here, let me also point out that this unbundler is what separates the data from the left and right side of the caches, and then sends it to the corresponding tag matching hardware. We need not limit ourselves to just 2 options for each byte in memory. We can extend the pattern of a two-way cache by making each line wider and adding more tag matching hardware. Here's an example of a 4-way set associative cache. Every byte now has 4 choices of where it can live. I actually wanted to do something wider like 8 or 16, but it didn't fit on the slide very well. Notice that the primary cost of adding associativity is size, not time. Those of us who work more with software than hardware are often naturally inclined to picture this associative cache searching through a line for a matching tag. And when we think about searching, it's hard not to picture a linear search. That's not at all what's happening here. All 4 tags are being checked in parallel, which means the only thing increasing the time of a cache hit is the size of the AND and OR gates on the right. And as we saw at the beginning of the semester, the propagation delay of a gate grows at most logarithmically with the number of inputs. In other words, increasing associativity has a relatively small effect on the time of the cache. But in order to compare all the tags in parallel, we need separate equality circuits for each tag. This makes the size of the cache grow linearly. There's also a second size-related cost to increasing associativity. The tag grows. Remember that the job of the tag is to identify which bytes are currently occupying a particular space in the cache. Video 46 discussed this in terms of pigeons. If we have 2 to the 32 pigeons, memory addresses, and 2 to the 20 pigeonholes, bytes in the cache, then there are 2 to the 12 pigeons competing for each hole, hence the need for a 12-bit tag. But if we allow each pigeon to choose from 2 holes, that doubles the number of pigeons competing for each hole. Thus, we need an additional tag bit. And this pattern, of course, continues. The more associativity you have, the larger your tag gets. Now remember that the offset, tag, and index bits must add up to the number of address bits. So if we add bits to the tag, we need to take them away from either the offset or the index. Which is it? Turns out it comes from the index. When we switch from a direct map cache to a two-way set associative cache, we conceptually double the amount of data on each line, which means if we're keeping the cache size the same, the number of lines is cut in half, thereby reducing the index by 1. So, how much associativity can you put in a cache? Well, as much as you care to pay for, which means you can keep increasing associativity as long as you're willing to pay for those additional tag checkers and the additional SRAM needed for the extra tag bits. In fact, if you're willing to pay enough, you can make your cache fully associative. That means the cache has the maximum possible associativity and consists of a single long line. Now be careful. You may be tempted to say that the data can go anywhere in this cache. That's mostly but not completely true. You still have to keep your blocks together because there's still only 1 tag per block. So in other words, you can only truly claim to be putting data anywhere in your cache if you have a fully associative cache and that cache has a block size of 1. So what is a typical associativity? How much associativity can we have before it practically gets too expensive? Most caches have an associativity somewhere between 2 and 8. However, this is determined not so much by cost, but by usefulness. This graph shows how the miss rate for a particular program varies with respect to both the cache size and the associativity. Notice that there's a significant decrease in the miss rate when going from a direct map cache to a two-way cache. That improvement is much smaller when going from a two-way cache to a four-way cache. Smaller yet when going to an 8-way cache, and barely noticeable when going from an 8-way cache all the way to a fully associative cache. That's why you rarely see a hardware cache that is more than 8 ways set associative. There's one last detail we need to address. When there's a cache miss in a set associative cache, we need to decide which data gets kicked out to make room for the new data. That's called the replacement policy, and that's the topic of the next video.